Gentlemen, let's at least prepare to fart around with the Z80 CPU. This is the one that we're going to be using. I did find a CMOS chip in my stack of junk. However, the IRQ pin is broken off of it, but I don't think we'll be using the IRQ pin, at least not initially anyway, so it probably doesn't matter. It's fortuitous that I found the CMOS version of this chip because I think the CMOS version is all static. The earlier NMOS versions of this CPU, which is all I thought I had, were dynamic, and that means that if you ran the clock too slow, they would lose their internal state. But I think, I may be full of shit, but I think the CMOS version is fully static, so we should be able to reduce the clock to like 0 and halt the CPU and run it real slow so we can see what all the different pins are doing while we're fucking with stuff and shit like that. So I think that'll be sweet, assuming that I am correct about this being static. This is certainly the CMOS version. This particular version of the CMOS version can run at up to 10 megahertz, but we will probably be running it at a maximum of like 250 kilohertz, at least initially, assuming this works. This particular chip was made in the 38th week of 1994. I don't even know if it works. It came off of a controller board out of a gas pump, so yeah, I guess we'll see. This will be a learning experience for both of us, I am sure, and I will likely do some stupid shit, which I hope that you all will call me out on. So, before we can do anything with this CPU, we have to have a clock source for it. So, I'm being a little cheesy with my clock source. Right here, you can see an ESP8266 module. It's running a modified version of the Blink example program out of Arduino. The only modification is that it's reading the analog to digital converter pin and using that for the delay between turning the LED on and off rather than setting it at 1 second. This is a 10K pot up here that's wired as a voltage divider. One leg of it goes to the 3.3 volt supply on the ESP8266 because this is a 3.3 volt module. Supposedly they're not 5 volt tolerant, but I've driven them with 5 volt logic before and it's worked fine. Do so at your own risk. Anyway, so yeah, the maximum voltage for the ADC though is 3.3 volts. So one side of the pot is wired to the 3.3 volt line and the other side is wired to ground. The wiper is wired up to the analog input pin on the ESP8266. It reads that analog value every time it delays between LED blinking, so we can turn this pot. You can't see through my hand, can you? We can turn this pot to change the speed at which our LED blinks, and I think the maximum speed that it'll run at is about 250 kilohertz. Let me get the right pin here. Or 250 hertz, I meant to say. No, it's running about 100 hertz there. Anyway, that's fine. As long as that CPU really is static, that shouldn't hurt anything. We can run the thing nice and slow, so we can see what the pins on the CPU are doing while we clock it. And then the GPO line 2 out of the ESP8266 module, which I think corresponds to D4 on the external pinout, is also the same GPIO that is wired into the built-in LED. So we can see what the clock is doing even when we don't have an LED hooked up to the clock output here. And that line goes over here into this 74LS04 inverter. And the reason for that is the the LED on the ESP8266 module is actually inverted from what it is in reality, and we want the on state of this LED to correspond to a high clock signal, so we have to have the inverter for that. But also, since we're powering this inverter off of the 5-volt rail from our lovely 1960s HP 6216 power supply, which actually works fine. I thought we were going to have to do a video fixing it because it probably wouldn't work, but lo and behold, other than being grossly out of calibration, it seems to be working fine. So yeah, that 3.3 volts is enough to read as a TTL high signal on a 5-volt device like this. So putting it through the inverter also converts the 3.3 volt logic output of the ESP8266 module into a 5-volt output, which is suitable for driving the clock signal of the Z80 CPU. And then we, for demonstration purposes here, we just go through a 470 ohm resistor out of that inverter and through an LED which is tied to ground. And when we turn on our magical whole power supply, the 5-volt clock output from this chip will start operating in sync with the one on the ESP8266 module. Happy day. Okay, let's see if we can make the Z80 do something. Well, first maybe we should examine the Z80 pinout and talk about how it works, this beautiful old boy from the mid-1970s. So, thanks to the internet and my ancient laser printer, we have a pinout of the lovely Z80 CPU, which maybe you can see better if I turn sideways like this. There we go. I can read that on the viewfinder, so hopefully you can read that as well. Alright, the pinout. Up here towards the top of the chip we have a bunch of address lines. These lines are used to select which memory or I/O location the CPU is trying to access at any given time. It puts a 16-bit binary word onto these 16 address lines, and that's how it selects a memory location. Think of them as, 65,536 little boxes that can contain a number between 0 and 255, and these binary digits select which of them little boxes Mr. Central Processing Unit is fixing to look in. Alright, like a data. Alright. Also, there are 8 data lines, which are not in order on the chip. There's a reason for that I was reading about the other day, but I can't remember what it is, so we'll have to think about that next time. But here we have D0, D1, D2, D3, D4, D5, D6, and D7. So I'll bet that's a lot of fun to break out in order to a bus. Huh, 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 huh. Additionally, we have a 5-volt power line here. Oh shit, my pin's not working. Oh, that's no good. Alright, there's a 5-volt power line there, and there's a ground right here. Those are the only power supply requirements for the Z80. Unlike some earlier ICs that required, funky ass voltages, like -5 volts and various varieties of 12 volts and shit like that. Wait, I have a black pen right here. Why am I using one with no ink in it? Just because it's the same as the rest of my pens that have colors. Alright, and then we are left with a bunch of control lines down here on the ass end of the CPU. So let's just go through those, not necessarily in order. This is a memory request line down here on pin 19. When it's when it's reading or writing to RAM, this is the line that it uses to tell us that, so that we don't accidentally read or write to an I/O device instead. Likewise, there is an I/O request line that does the same thing for I/O devices, like your keyboard or your screen or whatever the fuck we decide to interface to it. So it can differentiate between memory and I/O devices. That makes the Z80 an I/O mapped CPU. Other CPUs, such as the 6502 and the 68000, are completely memory mapped. They don't have an I/O line. They just treat all of their devices as memory. So you hook your keyboard into the same area that your RAM is in. It actually simplifies some things, but I guess inside the CPU wise, I guess it makes it a little more difficult to interface to things. But anyway, I digress. We also have read and write lines. Both of these lines here are active low, by the way. That's what the bar on the top means. That means that they're normally high, but when they are asserted, they go low. So yeah. We also have read and write lines over here on the other side. Those do exactly what you would expect when the CPU wants to read data from memory or an I/O device. It asserts the read line, which again is active low, which means it goes low. And when it wants to write data to an I/O device or to memory, it asserts the write line. Yay. Now there's also this M1 line up here. This indicates that it's in the first of four. Well, sometimes there are only 2 or 3 cycles, depending on what the Z80 is doing. At least according to the book, it's kind of confusing. This line is asserted during certain parts of the bus cycle, which generally, at least for memory reads, takes 4 actual clock cycles. But M1 is asserted along with the memory request or the I/O request line to indicate that it's in the midst of an instruction fetch, I think. We'll get back to that when we need to. I'll have to read the book again. I may have forgotten what I'm talking about and be bullshitting you, so don't take that for serious too much. Okay, up here we have a refresh line. That is used to refresh dynamic RAM. The Z80 was kind of a funny CPU in that it included memory refresh circuitry in it. So that line that happens during the T4 clock phase, I think 3 and 4 maybe. Anyway, yeah. So it can control dynamic RAM itself rather than having to have some external DRAM control circuitry, which is kind of cool, right? Here we have the reset line. That's used to reset the CPU. That clears out its internal state and starts it at address 0, fetches an instruction, and begins execution. Not only does that need to be asserted when we actually want to reset the CPU, you know, like by hand or something, we also have to assert the reset signal at power on somehow to put the CPU into a known state. Otherwise it powers up with just like shit in the registers, like random cosmic noise and fuckery like that, and it'll just crash immediately. So in order to get the CPU going the first time when power is applied, reset has to be asserted at power on. And we'll be doing that by hand at first, but there are ways to design little circuits that monitor the power rails and automatically do a power on reset, and we'll probably work on that later. But that's not relevant at the moment. Now, over here on this side, we have an interrupt line and we have a non-maskable interrupt line. Now, the interrupt line, it can be disabled in software. So you can disable interrupts here. Generally what happens is when a device has some shit that it wants the CPU to do, read data or write data, when its state is changed, an external device on the bus will assert this interrupt line. And if the CPU has interrupts enabled, that will make it stop what it's doing and vector to an interrupt handler magically. which will handle whatever's going on causing this interrupt, and then it can magically return to where it was executing to begin with. So that can be used to greatly speed up certain I/O operations and make things more responsive, because otherwise the CPU would have to keep polling the device, like asking, do you have some data for me? Do you have some data for me? Do you have some data for me? And most of the time the device would be like, fuck no, leave me alone. Quit, leave me alone, man. Which is very inefficient. I mean, that wastes a lot of CPU time doing shit like that, right? So we don't want to do that, and that's what the interrupt line's good for. The device can say, hey CPU, pay attention to me now, and the CPU can just ignore the device the rest of the time. Now, likewise, the non-maskable interrupt is similar to the interrupt line, except it cannot be disabled in software. Anytime that this NMI line is asserted, the CPU just automatically vectors to some predefined interrupt handler location. Maybe it might be memory location 66 hex, but I can't remember for sure off the top of my head, so don't quote me on that. I may be full of shit. But anyway, yeah, non-maskable interrupt. That's what that's for. Now, this halt line is asserted by the CPU when it executes the halt instruction and shuts itself down. And then the CPU just ceases execution until an interrupt happens. We won't actually be using this in our playing around, I don't think, but it may factor into things later on someday. Like if we start fucking around trying to make TRS-80 Model 2 CPU cards one of these days. Then we'll probably just have to hook it to the bus. I can't remember if the Model 2 actually uses halt for anything or not. I think it uses wait for, I'm not going to just talk out of my ass, never mind. Alright, so over here we have two lines, bus request and bus acknowledge. Those are both used for DMA cycles. So a device, an external device, kind of like interrupts. Alright, so an interrupt, like the device is like, hey, pay attention to me, CPU, and then the CPU is like, okay. The DMA is kind of the same thing except with RAM. What happens is when a device wants to directly access without going through the CPU, it can just directly read or write to RAM itself, rather than the CPU having to like read something from the device and then write it to RAM, and read something from the device and write it to RAM. See, that's slow, you know, like it can be much faster if the device can just be like write to RAM and then be done, right? So that's what these bus request and bus acknowledge signals are for. The device that wants to perform DMA asserts the bus request signal, and the CPU finishes whatever operation it's doing at the time, and then the CPU asserts the bus acknowledge signal and disconnects all of its data, address, and control lines from the bus. I mean, other than the bus acknowledge line, obviously. Completely disconnecting itself. It tri-states itself off of the bus so that it doesn't interfere with the device directly accessing RAM. So that's how DMA works. And then finally, pardon me, I must have the coof. Finally, we have the wait line. And this is an interesting line. I guess the 8080 probably implemented this. None of the other CPUs that I've personally farted around with have had a wait line like this. It's kind of unique from my perspective to the Z80. But what this does is when a device, be it memory, like slow memory or slow I/O device that can't keep up with the CPU's clock signal, which we forgot to mention, we'll talk about that next, I guess. When the CPU is trying to access something too slow to keep up with the CPU's clock, whatever it is, whenever the CPU immediately tries to read from it or write to it, whatever that device or memory is can assert the wait signal. And what happens then is the CPU just goes into an internal loop, wait states. It just keeps executing its own internal wait states any time that wait line is asserted. So that gives the slow, ancient, like 1970s RAM time to put its data on the bus, or the printer or whatever, time to like write a character to a page with a daisy wheel or whatever, and then when the data, when the device has successfully like read the data or put the data, latched the data onto the bus for the CPU to read, then that device can deassert that wait signal and execution continues. But this doesn't halt the CPU like stretching clock cycles would. It actually puts the CPU into an internal loop, presumably because the first versions of the Z80 were, like we discussed previously, dynamic, so they had to, you know, do their own shit inside so that, you know, it didn't lose its internal state. Now, it's worth mentioning that when you assert the wait line, that also disables the memory refresh. So if you've got a device that's asserting wait for too long and you're using DRAM, you can lose the contents of your RAM if you assert wait for too long. So that's not good. So one must be careful using wait states and dynamic RAM at the same time. And then finally, since we forgot to mention it before, we have the clock input. That's just, you know, whatever system clock you're running your Z80 at, your clock generator that we built up there before. That's what that goes into. So there are all of the pins on our delicious CPU. It's quite simple compared to modern CPUs, and that wait line especially makes the Z80 very, very easy to interface to. So I think that will make this a very pleasant project, especially if the CMOS version that we've got up there really is static and we can stretch clock signals indefinitely. So now, armed with our newfound knowledge, perhaps we can make the Z80 do something exciting, maybe. Or maybe I can just let the magic smoke out. I don't know. Let's see what happens. So first off, I guess we probably ought to wire the CPU to the power rails. That would really help. That would really help it work a lot, wouldn't it? Yes. So let's make a big insulation mess all over the place. Now, how do we do? What did we say? The 5-volt inputs on pin 11 on our breadification board. That's going to be right here. I made my fucking wire too long. I wish I had that problem with the ladies. Obligatory dick joke. We can't have an old computer fun video without the obligatory dick jokes. What would life be without them? Now the ground is on pin 29, which is directly opposite pin 12, which is going to be... I'm trying not to push my skeevy head in front of the camera. That should be pin 29 to ground. Very good. Now we're going to have to hook up our clock signal, so we'll pull our LEDs off of here. Perhaps we should just use a jumpification wire for that, and then maybe we can make it not suck later sometime. That's going to be the output of our gatoroo, right? Going to pin 6. 1, 2, 3, 4, 5, 6. There's our clock signal, and oh, that's not going to be electrically noisy, is it? Since we're running the clock so slowly, hopefully it won't matter. If worst comes to worst, I can put a resistor across there to try to dampen the noise a little bit, and hopefully it'll be running slow enough that the rise and fall times won't be all fucked up. I guess we'll see. Okay, so now we've got a clock and power to the CPU. We're going to have to be able to assert the reset signal to get the CPU operating as it should initially. So we're going to connect reset high with a 10K pull-up. So reset is going to be pin 26, which is opposite pin 15, which is going to make it to this one. We'll pull it up to 5 volts with a great big old long 10K resistor. That won't be electrically noisy, will it? And then we'll hook a fly wire in there, and we'll just stick it up here somewhere out of the way where we can quickly unplug it and touch it into the ground plane there to reset the CPU when we power it on. Right! When you power the Z80 on and then reset it, it will immediately do an instruction fetch cycle at address 0. It will fetch whatever instruction is at address 0 and execute it, as well as increment the program counter, which is the address that it's looking at for the next instruction. So we want it to execute some instruction, but we don't have any RAM hooked up to the CPU for it to, or ROM or anything, for it to read its instructions out of. So we're gonna cheat. We're just going to use some wires to wire all of the data lines to ground, because the instruction signified by all zeros happens to be the no-op instruction. Very handy that. The Z80 is quite handy like that. Things like that, just the way it does things like that is interesting, isn't it? So let me wire all of these data lines to 0, and then I'll be back. We got all of our data lines wired to ground. Okay, we've got our reset line pulled high through a 10K resistor, and we've got our fancy reset switch right here for when we need to reset the CPU. Now I've also tied bus request, wait, interrupt, and non-maskable interrupt high, because if they're floating and the CPU reads any of those as low, it'll do some funny shit that we don't want it to do. So what's going to happen now, assuming that I didn't do something stupid here, is that it asserts the memory request line and the read line, and tries to read the instruction out of memory location 0 by placing the address 0, the number 0, on the address lines. So it'll be all low there, alright? And then it tries to read it from the data bus, D0 through D7. Since all of those lines are tied to ground, it will read a 0, which happens to be the opcode for no-op, no operation. And then it'll execute that no-op, which does nothing other than increment the program counter. So then the next cycle, it'll place a 1 on the address bus, trying to read the instruction at memory location 1, since it's finished executing the one from 0, that no-op, and it'll of course read another no-op. And then it'll execute it, and it'll try to read from memory location 3, it'll find another no-op, it'll execute that, it'll go to 4, it'll go to 5, it'll go to 6, it'll just keep counting up indefinitely on the address bus. Let's wire the first 3, the first 3 address lines out here where we can get to them, and then we'll try to do something fun with them. That's right next to the ground, yeah, so that ought to be right. We'll get them down here where we can get to them a little more easily. There's A0, A1, and A2 right there, and then we're going to take some 470 ohm resistors, and we'll just tie those to ground. These are current limiting resistors for these LEDs. It doesn't matter if they're in front or behind of the LEDs, it just happens to be easy in this case to put them behind, because we can use them to tie into the ground plane here instead of using a jumper wire. It's just because I'm lazy and I don't want to cut more wire off of my spool, which is almost empty anyway. And I'd have to take apart my Apple II Pi breadboard over there that's been sitting there for 2.5 years or whatever. Anyway, then we can plug the LEDs in. Now, the longer lead on the LED is the anode, which is the positive side, so it goes towards the lines on the CPU, and then the short one, the cathode, the negative side, goes through the resistor to ground. So we'll plug all 3 of our LEDs in like that, and then we'll bring these lines over and plug them into the anodes. Did I get the right? Yeah, that's the right one. The anodes of the LEDs, like so. And then we will power up our clock generificator and get ready to hit reset with our fancy reset button here, and power on the bench supply. And if we're very, very lucky, it'll actually work, and if we're only very lucky, it won't work, but the magic smoke won't come out of anything. So I'm pretty sure this is the only CMOS Z80 I've got, so I hope we don't blow the son of a bitch up. And then let's hit reset. Oh, maybe we don't need to hit reset. I think it's working, boys. Hot diggity. Yep, it's counting up in binary from 0 to 7, and then of course it's setting the next bit of the address bus. But as far as the 3 lines that we're looking at here, it's just going to count upwards and repeat indefinitely. And we can adjust our clock speed there a little. See, 4 clock cycles for each instruction here. It worked. I figured I'd fuck something up. Oh, well, we'll fuck something up next time, I'm sure. Perhaps I should order a few more of these static Z80s. They must be static, or it couldn't ever run at a clock speed this low. Yeah. Alright, well, we know the CPU works, so this would be a good way to test any Z80s you've got in your shit bin. So, rock and roll, boys. Next time, maybe, I have a confession to make. Which is kind of funny. I've never in my entire life written a single line of Z80 assembly language. I've written C for the Z80 using SDCC, but I've never in my entire life touched Z80 assembly. So that's going to make things interesting. I guess since we're delving into this deeply, I might as well learn it. It can't be that hard, right? So next time, well, before next time, I'll do a little research and some testing first. Make sure I know how to do it. Next time we will try to interface a ROM to this thing and then make it do something. I don't know what. We'll hook a ROM to it though, and then once it's doing something with a ROM, I've got a Z80 SIO chip in another one of those gas pump boards over there that CPU came out of, but it's soldered in instead of socketed. So we'll desolder that SIO and try to interface it to the Z80. That's the serial I/O chip, and once we've done that, we can stick a Max 3232 or 2 on it and hook it to a serial terminal, and then we'll have a method of input and output. And then we can put some RAM on it and actually write some software that does shit. And that'll be pretty exciting. That won't be all in one video, of course. That's kind of the direction I want to go. And I'm going to have to build a better clock generator too, like a real clock. I bet there's probably I'll bet there's an oscillator pot on one of those gas pump boards that I can just desolder, like a good slow one, like a 4 megahertz oscillator pot or something like that. Although, If we're going to stay on breadboard, it ought to be lower than that. Like 500 kilohertz or something is probably the most we can get on breadboard before the edges start getting shitty. I don't know, what do you guys think? How fast do you think we could run this thing? Here's the fastest this thing will go. That'll make for a pretty slow serial connection. But I guess that's alright. Whatever. Well, there we go, boys. We've essentially built the world's shittiest 3-bit counter. We can give ourselves a pat on the back and win a fucking Nobel Prize. Yes, sir. Anywho, yeah, if you guys are following along at home and trying to build this yourselves, I will put a copy of the code that I'm using on that ESP8266 to generate the clock up on my brand new website, ocfco.net. Yes, sirs. So check that out. It's newfangled and innovative. Yes, and it's getting late now, but maybe by like tomorrow evening or something like that. Let's say day after tomorrow evening, maybe. If you want to try some of this shit yourself along with me, I'll see if I can whip up a schematic of this. It's not all that though. It's just I think it's D4, whatever GPIO2 is on here, is what the clock signal comes out of. You just have to invert it with a 5-volt device, and then you just wire your pot as a 3.3 volt voltage divider to the analog pin, and that's that. And the rest of it I think was straightforward enough as we were doing it here. You can figure it out. Yeah. Alright, cool. I'll see you all next time.